at CFA Harvard for her postdoctoral fellowship. And since 2001, she's been at Northwestern and has been the co-founder and director now of the Center for Interdisciplinary Exploration and Research in Astrophysics at Northwestern. She has received a number of awards. I will not list them all because it would take too long, but one of the noteworthy ones, or a number of them, are the Packard Fellowship, the Heinemann Award, and the Hans Bethe Prize from the APS. Her research spans a number of venues in understanding the birth, life, and demise of compact objects in astrophysics in binary systems across the whole electromagnetic spectrum, and very excitedly over the last couple of years, also the new space that has been opened up in terms of observations in terms of gravitational waves. So we're excited to have her here today. She will tell us about the dawn of gravitational astrophysics.
Thank you, Mario. Hi, everybody. Thanks for coming today. It was a pleasure to visit the department today. I had a great time all day long through my meetings with students, postdocs, and friends and colleagues as well. So it's always exciting. I've given now talks, of course, on the gravitational wave discoveries for many times since 2016. But it's always exciting to tell the story of how our lives have changed for the past couple of years, completely transformed. And in some ways, hopefully, we have transformed physics and astronomy as well. I always like these days to start my talks, whether they're public lectures or physics colloquia or astrophysics colloquia, with this picture. This is the Chicago skyline. And then on top of it, to scale, this is the edge of a neutron star, which we prepared at Northwestern for the announcement of the double neutron star merger that we made last October. And I love showing this picture, partly because it was made at Northwestern, but partly because when the New York Times had their main article announcing the double neutron star discovery, they used this picture, and I know Dennis Overby was really pained to have to show the Chicago skyline on the New York Times. It's the first time I make this joke in a New York City audience. And thank you for being polite and laughing. But I can tell you that it's a big hit anywhere else I make that joke. Okay, so I would like to today give you an overview. I know you've had speakers. I know Ray was here about a year ago. And maybe some of you attended Sheila Rowan's talk a few weeks ago. So I'm going to ask you to silence your cell phones. And what I intend to do today, hopefully and not run out of time, is give you an overview of our LIGO discoveries, both in the black hole space and the one discovery, of course, in double neutron stars. What I will not do is try and tell you everything we're learning. I will not try and give you an overview of the detectors. I don't work. I'm not an experimentalist. I am not responsible for these amazing detectors that have achieved the most precise measurement ever done in science and engineering. And I will, but I will focus on the astrophysics and the excitement in connection to astrophysics. So we're going to talk about the black hole discoveries with LIGO that are up here in blue. And now in this plot, we're placing them in the mass scale. The x-axis has no meaning other than not having overlapping circles on top of each other. So the blue are the masses we have measured with the error bars for various black holes with LIGO. Purple are the black holes we knew from X-ray astrophysics until now, and you can see the LIGO black holes cover a wide range in masses. Our first discovery was quite massive, but now we're reaching down to below 10 solar masses with the LIGO observations. And then the one double neutron star detection that we had a week before the LIGO detectors and the Virgo detectors closed up for our next upgrade lies down here. two neutron stars, they came together. We got the gravitational wave signal plus electromagnetic signal, of course. We are not sure what formed at the end. And then the rest of the yellow circles here are all the neutron stars we have measured in X-rays and primarily in radio observations in the past several decades. Okay, so that's the big picture. I want to highlight that, of course, I stand here as a member of the LIGO scientific collaboration, and this work would not be possible if all of us didn't work for many decades as a collaboration. So lots of institutions are represented here, and I need to, but I want to acknowledge, of course, the work of hundreds of people, scientists and engineers that contributed over many decades. This is a quick flash. I won't go into any details of this timeline, but I do want to remind you that the LIGO concept goes back to the early 70s. It became a real concept, really, with Ray Weiss, Ron Driver, and Kip Thorne. Thoughts about laser interferometry and how it can be used for gravitational wave detection pre-existed these three. In Glasgow, in Germany, and in Russia. But these three made it a real concept. It became an actual National Science Foundation project. In the 90s, site construction started in the mid-90s. By the 2000s, we were collecting data with what is now known as the initial LIGO detectors, but we knew that the detection was basically a very optimistic expectation. And at the end of 2010, initial LIGO operations ended, and we reopened our detectors with advanced LIGO in September 2015, and that's when we received the first signal of the two binary black holes. So we got the first signal that you see here in gravitational wave strain as a function of time. We're going to revisit this in a minute. The next big announcement, big signal visited us in August. We announced it in October 2017. And of course, these big discoveries led to the Nobel Prize being awarded to Ray and Kip, I already mentioned, and also Barry Barish, who Barry in the 90s, late 90s, basically made the collaboration a real project and got us to the point of succeeding in terms of sensitivity and eventually reaching the detection stage. I joined the collaboration back in 99-2000, and for some reason it's not marked in this timeline. But I was a postdoc at the CFA at the time, and for about 1 year, Harvard had the LIGO group. The group was me, and then I moved to Northwestern, and I did join the collaboration part-time, reluctantly, against the advice of all my mentors, who told me that I should not do this because LIGO will never observe anything, and I will destroy my career if I do that. So I didn't destroy my career, but I did join part-time, and I kept doing X-ray astrophysics and still do for a long time. But it's been a thrill and a privilege to be a member of this collaboration. My group at Northwestern focused for several years, and still, of course, that's our main focus, is really the astrophysics of LIGO sources. In terms, we developed for many years models for how compact object binaries form from stars. We made predictions for what the LIGO detectors will actually see, and now we focus on interpreting the detections we have at present. But at around a little over 10 years ago, I shifted and started a data analysis subgroup inside my group. We did a lot of method development. Right now we work on a lot of Bayesian method development and also machine learning for detector characterization. I actually became an observer in gravitational waves only. We also work on data characterization and detector characterization, but our main passion remains into trying and understand measure the source properties after a detection is made, after the signal is recognized in the data. How do we actually measure the properties of the source? And that has been our focus for over 10 years at Northwestern, especially how do we measure the spins of the compact objects we are recognized in the gravitational wave signal. So I want to highlight the people who have contributed in this work in a collaboration of 1,000 scientists and engineers. The people often get lost. For astronomy, this is very unusual, so I always want to highlight the people. Right now, this is the group, colleagues of mine, faculty colleagues of mine. Selim, I'll mention quickly, works on third generation technology for detectors. Shane and I are both faculty working on data analysis, but my young kids right now, I always call them kids and they don't like it, but I'll keep doing it. So one postdoc and 4 graduate students right now. And they all worked and they were at the center of these discoveries the past 2 years, and I couldn't be standing where I'm standing here without them. But the work in the group really also relied on these 5 other guys there. Some of you know very well. Will Farr is coming to the area in a couple of months as a Stony Brook faculty after leaving a faculty position at Birmingham, Stony Brook and CCA, I think. And they are partly responsible, these 2 postdocs in my group and these 2 graduate students from Northwestern, they're partly responsible for making me a data analyst and an observer in gravitational waves. So thanks to all of them, I can tell you the rest of the story. So right now we have 5.85 binary black hole detections, and the reason we don't have 6 is because one of these detections is not a 5 sigma detection, it's only a 2 sigma detection. It was the second event right after the first event, well, a couple of months later, no, a month later. And honestly, until the second 2 sigma event came, I wasn't 100% convinced that the first event was not a blind injection, a double, triple blind injection. Because the first event looked a bit too perfect to be believable.
It was an injection by God.
Yeah. God. So we didn't announce until February, but already in October we had this little guy here, and that was making us all breathe. And now we have this full set. We can measure masses, as I said before, and with the use of numerical relativity simulations, we can also constrain the final mass of the black hole that is forming at the end of the merger. There it is. And now I'll show you the signals that we receive in a number of different representations. This is really the hardcore way of representing our signals. This is frequency here in the LIGO band, so the gravitational wave signals. Think of this as part of the electromagnetic spectrum. This is part of the gravitational wave spectrum. LIGO is sensitive to frequencies from a few tens of hertz to a few several hundreds of hertz. This is our 2 noise curves from the 2 detectors in Louisiana and Hanford. And the vertical scale here is a particular expression of the amplitude spectrum for the gravitational wave strain in such a way that the visual relative height of the signal with respect to the noise gives you a sense of the signal to noise ratio. Okay, so the height of these curves, which are the signals, they're coming in with pure regular in spiral or well described by post-Newtonian expansion with no higher order effects coming into play or any dynamical numerical relativity effects being important. They enter the LIGO band. And then eventually, as they approach the merger, we get a bump in the gravitational wave amplitude, and then they shut off as we get the single black hole to form, initially it has to settle. It's still disturbed. There is quadruple emission still emitted by the final black hole. Eventually it becomes axisymmetric and the whole gravitational wave signal shuts off. The various signals are identified here in different colors. The higher the black hole mass is involved, the shorter the frequency range that we see from the signal, the more extended, the lower the mass is, the more extended the signal is. Another way to look at the signals again, the lower the mass is, the longer the signal lasts in our LIGO band. So these are again the 6 or so binary black holes. The first one is the shortest, a fraction of a second, 0.2 seconds. The latest, this one was detected by 3 detectors, 2 LIGO and the European detector as well, the Virgo detector. And the couple of the lowest mass systems lasted a couple of seconds. The last one here is the binary neutron star. You see it extended for a couple of seconds. It really extended to 140 seconds. Okay? Lowest masses.
What does LVT stand for?
LVT stands for LIGO Virgo trigger, while GW stands for gravitational wave signal. There's no S anywhere. Okay, so everything with GW in our statistical analysis exceeds a 5 sigma significance. Okay, and I don't have any slides today for interest because I'm focusing on the astrophysics and not the how we actually make the detection, but I have extra slides if anybody's interested for how we make the 5 sigma statement. All right, so I'm gonna now focus on how we, what do we learn from the gravitational wave data? What do we learn from these gravitational wave detections? And I'm gonna go through a number of conclusions and measurements we make. And feel free to interrupt me along the way. You don't have to wait along for the end. One thing we do, of course, one of the primary goals with these detections was to test as best we can general relativity. And of course, you all know that there is no surprise, at least so far. We haven't found any measurable deviations away from general relativistic predictions for how the gravitational wave signal from 2 inspiraling black holes and the final merger should look like. I should make the point by showing you these 2 first firm detections from September 15 and December 15, that these are allowing us the first ever strong field GR tests. And one way to express this and highlight what do I mean with strong field GR is that if we assume the black holes are moving in a Keplerian orbit, which they're not, of course, but if you transform your thinking into that concept, then you can put their orbits and say they're moving into some Keplerian orbit with a certain velocity, and that velocity for these 2 systems, by the time they're approaching the merger, it starts in the beginning of the LIGO band to be 30% of the speed of light, and eventually reaches and exceeds 50% of the speed of light. For the other, second signal also exceeds 50% of the speed of light. In comparison, the best general relativistic test we had was from up until that time, was from the double pulsar, the system that has 2 neutron stars, and we observe, or at least we used to observe, both neutron stars as radio pulsars. The relative velocity in the orbit, in the orbital motion of those 2 neutron stars was 0.1% of the speed of light. Okay, so this is really as strong field as we have ever probed observationally or experimentally. And with the LIGO data, we decided that as a collaboration, we will not try and test every alternative theory of gravity that might be out there, but instead we will take an approach, non-parametric or whatever you want to call it. It's not really non-parametric, but an approach that doesn't focus on any particular alternative theory, but instead we're going to ask the question, can we see any deviations away from GR? Can we measure any, or what constraints can we set on any quantitative deviations? And we did 3 main tests using the first binary black hole. And I'm going to show you also the latest results with the second binary black hole detection. Why is there nothing particularly exciting or big news coming from the others? It's because the others have lower signal-to-noise ratios. And honestly, the strongest tests are really coming from that first one event, because and the combination of the first and the second, because that's where we have the strongest signal-to-noise ratios. Okay? So I don't want to spend, I have a lot of astrophysics to tell you about, and this is not astrophysics, but it is a physics colloquium, so I'm going to go through these slides very fast, because it is a negative result, but I'm happy to answer detailed questions down the road. So we did a couple, we approached things in 3 different ways. We first asked the question, if we know how to characterize our noise in the data very well, and then we asked the question, if we fit our signal with general relativity waveforms, and we remove the signal, and then we look at the residuals, do the residuals look any different than our noise, our regular noise in segments of our data away from the signal? The answer is no, and this plot is expressing exactly the statement I just made. Okay, so I will not describe the specifics, but we have a quantitative way of giving the answer I just gave. No, the residuals look statistically exactly like noise if you remove the GR waveform. Then this is a little more complicated, that says if I assume GR is correct, then I can measure the final mass and the spin based on my data, and I constrain it to be inside the solid black circle. If now I don't assume anything about numerical relativity and general relativity, I only constrain the final mass and the final spin from pure post-Newtonian expansion, so no dynamical general relativity simulations, or from quasi-normal mode, so perturbation theory. Do the constraints on these 2 parameters overlap with my numerical relativity constraint? The answer is yes, therefore I see no inconsistency with my numerical relativity analysis. So that was another way we approached the question. The third way was to use the post-Newtonian expansion of the gravitational wave phase. If you do that, you get coefficients in this kind of series in the terms, and then you ask the question, okay, can I constrain any deviations away from these coefficients? How much of a constraint can I put? And the constraints are not fantastic. They're actually kind of pathetic quantitatively, if you think about it, if you look at the x-axis. These are the quantitative constraints we can set on the y-axis. This is the various p-n orders we can reach. First, I'm going to make the point that this is first with our initial, very first binary black hole. And you see the p-n order here. And these are how high can these deviations be? 10% versus the GR term, 100%, 200%, I'm sorry, 1,000%. Am I going well? Yes. Okay. So these are lots of orders of magnitude here, okay? The point I want to make is that first, for the first time, we can actually set limits on these higher order terms. With a binary neutron star, which is this one, we could not set any limit on these higher order terms. So these are the limits on the higher order terms. And then we can beat the limit for the double neutron star, the 2 limits at half p-n order and first p-n order. We can't beat it on the pure Newtonian term because we had only 0.2 seconds to make our observation. The double neutron star have had 15 years to make their observation. Okay? So we can't win over time. But already with 0.2 seconds, we are setting better limits on these two terms. And with the second good detection, which is a combination of the two, the purple dots become better than the original blue squares. That's the message. Okay? So in 3 slides, I'm showing you different ways of addressing the are there deviations away from GR based on our data? And the answer is not significant, not measurable. Okay? We just have upper limits. They're not all fantastic upper limits, but they're the tightest we have right now in the strong field regime. So now I'll transition into the area where my group and my interests and astrophysical interests are most closely connected. And that's where the transformation is really happening for astronomy and astrophysics with binary black holes. So what the gravitational wave signal is allowing us to do is extract 3 core quantities about the sources. We can measure masses for the black holes. We can measure spins for the black holes. We can also measure distances for the sources, which in astronomy is fantastic. Okay? Distances are so difficult to measure in astronomy, as we know from cosmology, but any field of astrophysics, distance is a challenge. So how do we make these measurements? Just to remind you, very, very briefly, I won't go into this formula in any detail, but just to remind you, what we really measure is a frequency as a function of time. So we get frequency of the signal and a frequency derivative from the gravitational wave data, and that directly, these two measurements directly translate into this chirp mass, which is this combination of the 2 individual masses of the black holes. Capital M is the total mass. So what we really measure is the curly M. Then, with the frequency and the curly M, and the peak of the gravitational wave strain, I can measure the distance. Because in gravitational wave astronomy, we measure amplitude, absolute amplitude. We don't measure power. Okay? And that gives us the distance along with the frequency and the frequency derivative. And that's key. So now we have masses and distance. Now, this all looks nice and simple. It's not that simple in reality. There's a few extra terms. There's extra terms that have to do with the inclination of the binary on our detectors that I'm hiding under the rug here. So there's actually a distance inclination degeneracy. There's terms here that have to do with the inclination. So we don't know how the binary is inclined with respect to us. So depending on if it's face on or inclined or edge on, we have that degeneracy there.
Are those degeneracies not broken by polarization?
They are.
Yeah. Okay.
So depending on how well we can measure polarization in the gravitational wave signal.
In the future, if you had enough antennae,
Yeah.
you could get it.
So we only have, so the 2 LIGO detectors were on purpose just tinily misaligned from one another. And the reason was, and I don't know if I'm doing it, I can't remember their exact orientation, but they're almost perfectly aligned, which of course kills polarization measurements.
Yeah.
But the reason was that if you only had those 2 detectors, the priority was we want coincidence. That was more important, so we can claim detection instead of measuring polarization. If you made them 45 degrees misaligned, you would maximize polarization measurement, but you would sacrifice coincidence, and that meant you may miss the signal. So Virgo is significantly misaligned, not optimally. So it gives you more polarization information. Additional detectors in Japan and India will give us more polarization information. So that will improve indeed.
How large a correction are these unknown inclinations? How much can it change
The distance?
Yeah.
I used to have a nice plot. I may have it in my extra slides. The polarization, and somebody asked me if I'll be using Blackboard, and I said no. But I'll use it anyway. Where should I use it? Under? I don't know, for the video. Anyhow, so the degeneracy is like V-shaped this way, and the distance is here and inclination is here, and it affects your distance by typically a factor of 2, sometimes much more. So, it's bad, but it's better than not having a clue what the distance is. Okay, sometimes it's better. To give you an example, the best distance we have measured, we had, which was fantastic because we had the Virgo contributing detector. It was 40 for the double neutron star. It was 40 megaparsecs plus or minus, plus 8 minus 12, or plus 12 minus 8, I don't know. So that was as good as it gets so far. All right, so extra terms, if this is all in the quadrupole approximation, if you go to higher Poissonian terms, then spin effects appear. And of course, we don't stop at these simple expressions. We use the terms that are affected by spin. They affect both the gravitational wave amplitude and the phase. And then, just like with the masses, we don't straight measure the masses. We measure some combination of the masses. With spins, we don't straight measure the spins of each black hole. We, in fact, measure a combination of spin magnitudes and spin tilts. And the combinations are given here, and I won't go into the details, but I'll tell you that these chi factors are basically expressing more or less the spin component, the combined spin component that is aligned with the orbital angular momentum axis of the binary, and the chi p component is the other component in the plane of the orbit perpendicular to the spin aligned component. So that's what we can measure. All right, so now these are again the 6 events on the mass 1, mass 2 plane. And you can see how well the mass measurements now happen. These bananas are basically giving you a visual sense of how well we measure chirp mass. These lines here are lines of constant chirp mass. So we measure chirp mass really well. The width of the banana is the error bar in the chirp mass. Where the banana will end depends on where what is the maximum frequency of the signal, where it can cut off. That's the total mass that dictates. The total mass dictates that cutoff. The total mass dictates really where this banana ends. But then when you ask astrophysically, what we care is the individual masses, what they are. The error bars are kind of big. Okay? So we don't get 10% errors on the individual masses. And then we are trying to measure, but really right now we're not measuring. We are trying to constrain, for now, the spin magnitudes of the black holes and the tilts. And this is what we have so far from our 6 events. And this is what we spent years in my group developing the codes for doing this measurement, okay? And for the life of me, I can't believe that I can't convince the collaboration to stick to one way of showing the spin disks you're looking at here. So that I can give talks like this and show you 6 disks from published papers, that they all have the same dynamic range, and I can tell you that what I'm showing you is what it is. The problem is what I'm showing you is not what it is. Okay?
Wait.
I'll explain what I will take my time. So I'll describe what the disks mean, but what I want to tell you is that the dynamic range of what is dark and what is light here versus there is not the same. Because different people wrote each different paper. and I don't control what favorite scale each person chose. Okay. Rant over, Vicky. So now, let me tell you what we're plotting. 2 black holes, 2 spin vectors. Each half circle is 1 black hole. So primary black hole, more massive black hole on the left. Secondary black hole, less massive black hole on the right. Then let's look at this plot that has the sort of the single nice dark region here. With each half disk, we're showing the spin magnitude from 0 to 1, maximal black hole spin, and then the tilt with respect to the orbital angular momentum axis. So perfectly aligned, 0 tilt, in the orbital plane 90 degrees, anti-aligned 180 degrees. Okay? So even though this might be misleading you to think that we're actually having a strong measurement here for the secondary black hole, here you're not getting misleaded, but this might mislead you. The reality is we can't measure spins for the secondary black hole.
I was confused. Is this just for the very first event that's the best
No,
data? or
these
is
are
this
the 6
first-
events.
Oh, I'll say. Oh, I see. Each one is a different event.
Yes, I'm sorry.
Sorry.
They are, yes, you're right. The names are not there. These are the 6 events, the 5.85.
And the uncertainty represents the uncertainty in the spin and in the mass as well. So
These-
you're not assuming a mass to get the spin.
Oh, this is the posterior samples
Right.
for the spin magnitude and tilt, and they are projected here, but they have been marginalized over the mass posteriors. So we're not assuming any mass. It's whatever, when we fit and do the parameter estimation, we do the parameter estimation in the full 15-dimensional space that includes the masses, the spin vectors, the distance, the orientation of the orbit, the location on the sky, everything. Okay?
And so you have full numerical simulations in this 15-dimensional space?
Correct.
Okay.
Yes. Yeah. That's what
So
we
it's like a
spend
huge
years
table.
developing.
It's a
No,
huge table,
so,
or-
well, it's not a table. We do Markov chain Monte Carlo, and we have waveform approximants that are calibrated based on numerical relativity waveforms. And then the waveforms at each point, as the Markov chain, I'm being too technical, I think, now, but if you know what Markov chains do, they walk into this 15-dimensional space. And for each point in the space, we calculate a new waveform. We calculate the likelihood, cross-correlation with our data, and then we decide what's the next step in the Markov chain.
And so
But the
effectively you're-
waveforms are not numerical relativity waveforms. That takes forever to calculate. They are approximants calibrated by numerical relativity waveforms.
That's all I was gonna say.
Yeah.
It's an emulator. effectively.
It's a, yeah, we call it an approximant.
Yeah.
Any other questions? Okay. Now, so we measure masses, spin magnitudes, spin tilts, and it turns out that the masses and the spin tilts especially are giving us clues. They connect to our astrophysical understanding of how binary black holes actually form in nature. And that's why we really care about making these measurements. Okay, and I'll come back to this point.
So in terms of future detections, so ideally you would like actually lower mass black hole merger to be able to measure the tilt.
Yes, so
better,
that's
because you
correct.
have many more orbits.
Absolutely. So
'Cause
how
that's
do
really
we
important.
measure the tilt? Maybe I can go into more detail there. The tilt basically, if the spin is tilted with respect to the orbital angular momentum axis, it's causing the orbit of the binary to precess. Okay? And as it's precessing, the inclination of the binary orbit with respect to our LIGO detectors is changing. And therefore, it creates modulations on the phase and the amplitude. And that's how we can measure the tilt. And these precession has its own period, different from the orbital motion. So the longer the signal is, the more of that precession modulation we can measure. So lower mass signals are going to give us more of a time in the LIGO band to see the precession effects. We need high signal to noise ratio, lower mass signals, but we also need a preferred line of sight, which is kind of luck, and the observational biases are hurting us because, I'll do it this way so you can see me, we get the high signal to noise ratio if the plane of the orbit is face on with respect to the detector. That's where we get the strongest gravitational wave signal. But if you're face on, then the precessional effects are minimized. So, you know, if you want precession, you want to be offline, face on. If you want high SNR, you want to be face on. So there's a bias in a small number signal, a small number sample. So right now, we don't have enough detections to catch the high precession systems. Yes?
What are the amplitudes that are possible within the precession? Is it enough to take you away from getting the signal whatsoever?
Can you lose the signal altogether because of precession? Yeah, under certain configurations and certain line of sights, yes. I don't have a quantitative answer for you of how often this is possible. Based on my educated intuition, is like you need very contrived configurations to get the signal to completely get lost. Basically, you need the envelope, the chirp. The chirp is, and I'm a horrible drawer, so forgive me, but the chirp is, like this, and then the modulation of the precession is trying to do something like this, and you want this to come down to 0. And that will happen for very contrived configurations.
Would you go as far as saying it's non-physical?
No, I suspect that there's probably some angles, sky locations, etc., and depending on the detector's positions that you might be able to get it. But I don't think it's a high volume in the 15-dimensional space. Yeah. Yeah?
Does C over GM squared represent an absolute limit for the possible spin? Because it's like an axis from 0 to 1.
C S over, so this is...
The scale.
No, this is 1, from 0 to 1. The whole C over... So the maximal spin is normalized to the mass of the black hole.
So that's a physical limit.
Yeah. Yeah. Otherwise, you get an open. You don't have an event horizon. Beyond 1, you don't have an event horizon. All right. The last thing we get out of these observations, if you have events that are transient, you can measure a rate of your events. Okay. So I'll say a few things about our rate. Somebody was asking, the students were asking me, so it's not 20. What did I tell you, 20 to 200? Here it is. The current statement is 12 to 213. And I told you, my memory is failing. All right, so I want to make a couple of points. We can measure a merger rate. We have 5 events. Even with 1 event, you can measure a merger rate. I'll make a couple of points without going into a lot of details. The merger rate, of course, has a statistical uncertainty. There's Poisson statistics, okay? We don't actually, Poisson statistics is, we use a Bayesian method of measuring the rate. The core method, I'll try to skip the details because I fear I'm probably running out of time. But we have a statistical uncertainty. So under certain systematic assumptions, we can derive a probability distribution function for how often these events are happening per year, per unit volume in the universe. Okay? And that's an astrophysically meaningful rate because there's models in astrophysics that make predictions about these things. So we can compare two models and exclude models, etc., etc. However, from our data, we can derive this probability distribution function on the rate, or the rate density, really. But we have to make an assumption for how much volume our detectors are sensitive to, and to answer this question, we have to know what is the underlying mass distribution of black holes in the universe. Because how much volume we can reach in black hole mergers depends on how massive the black holes are. Therefore, we need to know what is the mass distribution of black holes in binaries in the universe. But of course, we don't know that. We can make an assumption, or we're extracting it the more binary black holes we're detecting. So for now, these are three curves for three different assumed mass distributions, but at the same time, in this case, if we assume the mass distribution is a power law, we're using our 6 events to measure the slope of the power law. So you can see now that we have statistical uncertainties because we have only 6 events. We have systematic uncertainties because we don't know the mass distribution. But as our sample grows, we are both improving our statistical uncertainties, but at the same time, we're improving our systematic uncertainties because we're measuring the underlying mass distribution. And that's the point I want to make. The specific numbers we have now are going to keep improving, and where we settle at the end, we'll find out, and then we'll have a clear, concrete statement about this rate that will constrain the models. I'll skip this one. These are specific models, and where are we in the rates? Some models overlap with the current PDF, some don't, but I'm gonna skip that. I will give you I'm looking for a clock. Where am I? Thank you. Oh my goodness. So I'll just say that for binary, ultimately from an astrophysics perspective, we're trying to understand how these binary black holes are formed, okay? And over decades before these detections, there's a lot of speculation in the field. There's a lot of things we don't understand. You think stellar evolution and stellar black hole formation might be a solved problem, but it's far from solved. So I'll just say that there's tons of different models, which I will not describe. They fall into 2 classes. Binary black holes can form from stellar binaries that went about their lives normally, nuclear evolution, and eventually formed binary black holes. Or black holes formed independently in dense stellar regions, and then the black holes came together through gravitational interactions, formed binaries, and the binaries merged. And under these 2 channels, there's there's sub-channels of how this happens, and does one dominate over the other? Is it a combination of these 2 different channels? Is an open question right now, and we're hoping that the LIGO detections will allow us to answer some of these questions. The mass distribution, the spin magnitudes, the spin tilts, the rate as a function of redshift, all of these are going to be clues that will allow us to answer these kinds of questions. This is a nice simulation done by a graduate student, now a postdoc at MIT. Where is my pointer here? Carlo Rodriguez, that shows an actual simulation of dense stellar clusters of black holes, and you see the black holes because we take into account the gravitational lensing. All right, this is what we can use. I just said in words what I'm showing here. I'm gonna skip this, and now transition.
So you would see a signal of a triple wiggle?
It's gonna be hard.
Yeah,
It's gonna be hard. Yes.
Right.
So
likely, I guess there would be
not with LIGO. Potentially with the space-based mission, we can see triples. So, all right. So in whatever time you're allowing me, I will try and tell you about the double neutron star. But here's what we're going to do. I'm not going to say anything about the electromagnetic emission from the double neutron star, because I know you have a local expert. You can ask him what we're learning from the electromagnetic emission, but also you've had other speakers, and I'm studying the gravitational waves, and therefore that's not my focus here. I will try to highlight a few things and skip a few others about what we're learning from the binary neutron star from the gravitational wave zone. Okay? So this is a collection of the key plots, but really the gravitational wave signal is right here. This is the chirp frequency as a function of time, increasing frequency, and then it stops, increasing frequency, and then it stops. It also becomes brighter. Here you don't see it, there you see it. So that's the signature of the chirp. On August 17th in the morning, the signal arrived. We looked at it within minutes, and it was 140 seconds. What you see here is about 30 seconds, because visually you can only see it for about 40 seconds, but our template fitting gave us a template that best fit the data for 140 seconds, and we knew immediately this was a binary neutron star, okay? Because nothing lasts that long, other than low mass, 1.5 solar mass objects. And Virgo saw nothing. Virgo, the fact that Virgo saw nothing while on August 17th, while on August 14th, Virgo had detected, along with the LIGO detectors, that for the first time ever, a binary black hole system, along with us, it was the first triple detection we had, and we knew, the world didn't know, we knew Virgo was working, okay? So we were puzzled at first. Everybody checked, was Virgo operating? Was there anything wrong with Virgo? All the tests came back. Virgo was perfectly fine. Why isn't Virgo not detecting a signal that was the strongest signal we had ever seen in LIGO data? It was a signal-to-noise ratio of almost 30. And how come Virgo had seen nothing? Well, Virgo had seen nothing because it was at a very particular part of the sky, and it was in the blind spot of Virgo. Okay? So that allowed us to localize it on the sky really well, and that, as soon as it became nighttime in Chile, we knew it was in the south. It looks like it's in the north here, but the mapping is anti-intuitive. As an ignorant theorist, I told my colleagues, why do you keep telling me it's in the south? It's in the north.
So we know exactly where it is because Virgo did not see it.
Yes.
That's right.
But we knew it was
But
working
you
well, and
should
we
have
checked that
okay.
indeed on that time after it was working well. It was all the checks of the monitors, etc.
So what
So-
was the search area here?
The search area was, I don't know if it's written there, I'm trying to test my memory. I think 28 degrees, square degrees. Okay, so as soon as it became nighttime in Chile, an optical source was identified. 20 days before, nothing was there, and then more and more evidence came. Part of the story, of course, we had already been alerted that independently, Fermi, the gamma ray satellite, had seen a gamma ray burst, like it had seen many of them in the past. A gamma ray burst that was coincident within 2 seconds, coincident with our signal, 1.7 seconds later than the end of our signal. They had seen a gamma ray burst, consistent with our extraction of the fact that this must have been a double neutron star. Okay, so I can tell you that within 2 hours, we knew we had woken up to a multi-messenger detection. All right. Okay, I'll just say that we're very happy that a year before this happened, we had hired electromagnetic observers at Northwestern, and therefore, next to my group, we also had electromagnetic observers leading their own effort of following up electromagnetically this event, and we were I was in heaven because I had told the administration of the university, we have to have observers in our group. We're going to have multi-messenger detections and we will be out of the game. And then we got this event, and Rafaela and Wenfei were leading inside the team as first authors in multiple observations. And I could go back to my administration and say, you see, it was worth it. All right, so my group ended up on the day of the announcement. The LIGO collaboration put out 6 papers. We write papers with 1,000+ authors. One of them had 4,000 authors, but the papers are written by 5 or 10 people. To be on the writing team is a huge deal. To chair the writing team is a huge, 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 huge deal. Some people hate you. And what happened about a week after the event, I realized that at Northwestern, one of my graduate students was chairing the team of this paper. My postdoc was chairing the team of that paper. And I was a member of this writing team, and my faculty colleague was a member of this writing team and of this writing team. And then I said, that's why we're just walking around like zombies. So I'm very proud of this team, because we're a tiny group in a giant collaboration, and we were heavily involved in 4 of the 6 papers. And
It's electromagnetics. They don't like you.
Yes. All right. So now I should be moving. Maybe it was telling me that it's time to jump some slides, Vicky. Oh, I know. It's this plot is giant because it has this glitch that our Livingston data had that I was gonna skip. Ask me about it if you want. There was always something that made life difficult. So just to give you a sense of sky localization, our previous sky localizations, giant arcs on the sky, 3 detector detection with real data from Virgo, binary black hole, no detection from Virgo, but Virgo operating. This is the double neutron star. Okay, we measure masses. I just want to tell you here that for the double neutron star, because the signal is so long, what you assume about the spins of the neutron stars actually makes a difference in what masses you measure. And if you think you know nothing about the spin of the neutron stars, you get the red probability distribution functions for the 2 masses, primary mass and secondary mass of the 2 neutron stars. And for sure, they're below 3 solar masses, but if you take them at face value, you measured a 2.5 solar mass neutron star, maybe. Okay? If you then constrain the spins to be the kinds of spins we see and measure reliably in double neutron stars, radio systems, then the PDFs on the masses become the blue things, which are consistent with the masses we measure dynamically in radio observations. So 1.5 solar masses, or 1.2, 1.3 solar masses. So we're pretty convinced these are actual double neutron stars. We can set constraints on the equation of state. Just like before, we don't measure the actual radius. We measure this combination of radius over mass to the 5th power. We can set upper limits on these lambda parameter for the 2 neutron stars, 1 neutron star, 2nd neutron star. The 90 percentile upper limit is here for the 2 different spins. The blue is the one I think is more realistic. Spins comparable to the double neutron stars we know in our galaxy. We exclude only a couple of extreme equations of state. Now I'm going to translate this into the classic mass radius plot.
So
yes?
given that we have so many orbits, we can't measure the spins directly from the gravitational wave signal?
There's no precession.
Okay.
You see no precession. And the reason is that probably the spins are tiny.
Alright.
Silence your phone, David.
But it doesn't,
Um,
so you can't set a constraint on the spins from
If the
node
spin
precession?
magnitude is tiny, you can't measure anything about spins.
Right, but then you can set a constraint. Or not? I don't get it.
You can set a.
The fact that you don't measure doesn't mean that they're tiny, hence you have some.
Oh, I see what you mean.
But they aren't.
Not
very-
because if they are aligned. So the problem is you can't in those spin disks. If maybe you don't measure anything because they are aligned, or
I
maybe
see.
because your line of sight is face on. So there's too many degeneracies. So you can't say for sure the spin magnitudes are small. So we just don't make a measurement. Okay. All right. So in terms of the radius right now, strictly speaking, that's the only statement we can make. We exclude these extreme equations of state up there. Upper limit on the radius 14 kilometers. However, we are working on better constraints on the tidal effects and signatures in the gravitational wave data. We have tighter constraints on the radius. They haven't been published yet. We're being very careful. Stay tuned.
But they're just upper
That's all I can say.
So is it just an indirect argument that you see the electromagnetic signal that says it's not too black hole?
Yes, correct. So as you can see, we cannot exclude 0 lambda values. So it's only the masses and the fact that we saw electromagnetic waves that says it must be a neutron star and not a tiny little black hole.
So now coming back to the first picture you showed of the neutron star, so you assumed it was a 14 kilometer, right? Or less than 14 kilometers.
Upper limit. It's an upper limit. So where is it? So we are excluding, the X means excluding everything to the right. Yeah. At 90 percentile confidence. Okay? All right, and then the last thing we measure from gravitational waves is the rates. Turns out, back in 2010, my postdoc Ilya Mandel and I put together a review of rates. We stuck our neck out and we said, we're gonna look at the best double neutron star rates, which at the time came from radio pulsars, and we're gonna, to the best of our knowledge and understanding of the radio pulsars back then, we're gonna call out what we think is the most realistic rate estimate. The rate estimate was coming from a paper I had written in 2004, so 6 years before. This was a review. So from 2004, we said in these units, the realistic rate to expect is 1 per cubic megaparsec per million years. Our current measurement is this. Still a big range, but certainly not the low end, and less than a factor of 2, about a factor of 2 below the high end. It's one event, and we're gonna see where we're gonna end up. But with the binary black holes, our peak hasn't moved. Our PDF has become tighter and tighter in the rate. Yes?
Do you take redshift into account in calculations about the rates?
Of the rate?
Yeah.
So for the double neutron stars, we're not sensitive. We are sensitive out to 80 megaparsecs, and rate doesn't matter. But we are working on, we're going to have to do that for binary black holes starting in 03, observing round 3. All right, skip that. Gamma ray burst implications, I'm going to skip them. New way of measuring the Hubble constant. We're very excited. There's nothing exciting to measure right now. Our measurement is much broader than anything people can do with cosmic microwave background or type 1a supernovae. But hopefully our systematics are extremely different than the other systematics. So we're hoping that eventually with more binary neutron stars, we'll be able to say something useful. I'll skip the work of my postdoc and my graduate student. We got the astronomy and gravitational wave community to write a 4,000 author paper. The paper almost killed me.
It's also a significant fraction of all the research active astronomers in the world, right? It's something like a fifth or something of all the research active.
So nominally speaking, so you can measure it in some way. It's 30% of the IAU membership, but a lot of these authors, about 700 or 600 of these authors of the 4,000 are LIGO scientists and engineers who are not members of the IAU. So, and then the electromagnetic follow-up, I won't tell you anything. As I said, you've heard it. It gives evidence for how heavy elements get produced in the universe, and it also tells us something about how relativistic outflows are being formed. So I'll skip my last couple of slides, but Andrew here has some very interesting results I saw today. And I'll just finish by telling you what to expect as soon as our new detectors, detectors are the same, but they're being upgraded now. Our new observing run is going to start later in the fall. And here's what we think is going to happen. For binary black holes, which are going to dominate our detections, we might be getting at least a few per month, but maybe we'll be getting a few per week. And I don't know how we're going to live through this, because already the ones we've had now keep us awake, and awake, and awake. And then double neutron stars, we may get up to 1 per month, which will be 10 in a year. The actual calculations with all the error bars, etc., are here. Double neutron star black hole obviously will be the third category to break open. Whether we're going to get it, high uncertainty, we really don't know the rate. So whether we're going to get it in this third observing run, we'll see. We don't know. That's where we are. Thank you.
What do you expect the search radius to be for that 1 a month neutron star? With
What do I expect the what to
the
be?
search radius to be for follow-up?
For double neutron stars, yeah. This assumes that we can reach out to 120 megaparsecs. We used to be at 80, so about 50% improvement in distance. So cube that in terms of volume.
But I think she's asking about square degrees.
About square degrees.
Oh, I'm sorry, the search area. Okay.
She's electromagnetic.
Yes. And I do have a plot of that. Assuming all 3 detectors are on, duty cycles okay, so assuming all 3 detectors are on, I know the design sensitivity will bring us down to tens, typical accuracy of about 10 square degrees. More like, I would say 20 to 50 square degrees, but the typical generic event that is not super high signal to noise ratio and it's not at a nice location, I would say 50, worst case scenario 100 square degrees. So,
It's good.
yeah. Yes?
If and when the space, detector goes up, what would you expect that it's like? Is there just going to be so many signals coming that it's just going to be like every second,
Well,
noise?
the LISA detectors, the space-based detectors, have different science goals. I'll start by saying there is overlap with LIGO only in the sense, exciting overlap, in the sense that LISA can see binary black holes before that eventually merge in the LIGO band, 10 years ahead of time, okay? So it's going to be a predictor for LIGO. Why are you laughing?
I'm laughing because 10 years before is a lot of events.
So there's
Yes.
10 years of events that are all showing up at the same time.
Because it's only the ones that are very close, they're showing up at the same time, but you can analyze them and find them that are highest and R, and you can see them as individual events. And there's nothing going on electromagnetically for those, so there is no craziness, okay? You just know they're there, and they're slowly evolving through the LISA band. The problem with LIGO is that everything is happening fast, okay? So we have to be up and whatever. But the other sources in LISA, there's stochastic background that is steady, and it's not going away, and it's not disappearing in 1 second. And then there is sources that are going to be there and drifting over years. So again, this is supermassive black holes, small compact objects falling into supermassive black holes. These are complete science that LIGO cannot address, cannot reach, but a different way of sort of operating and doing gravitational wave astronomy.
Last question. I want to ask a little about the collaboration and specifically about the data analysis and how much like it might be like or not like high energy experiments. I mean, are there different teams and how many are there and are they working?
I'm happy.
Do they work privately on each thing and
No.
then compare data after they've each completed?
Yes. So we have. The data analysis is split into 4 groups. So we have the binaries group, the burst group. Then we have 2 other groups who haven't had signals, the monochromatic sources looking for gravitational waves from a neutron star that might have a pimple, a little mountain, and have non-axisymmetric structure that will give you gravitational wave emission, and a stochastic background group. So inside each group, we have over the years come up with different ways of analyzing the data, looking for the same type of source. So we have different pipelines. And then we tend to basically, it's a combination of different groups coming with their ideas, but then bringing them to the table and saying, in the past at least, it was, yeah, we have an idea for how to analyze the data and look for this signal. Can we try it? And until some group or subgroup had to demonstrate that this has a hope of being useful, nobody was paying attention to them. Then if you could convince the collaboration that what you're doing might be useful, then you became part of the blessed pipeline.
But they're not really, I'm thinking of this criticism that came out of, was it Denmark or somewhere?
Yes,
Europe,
absolutely.
about the,
but by the time,
and I'm just interested to know what your response is
and I'm
to what extent
happy
they
to
were
address it.
thinking.
Yeah. So first of all, by the time we reached the point of actually, claiming a detection, we had in the search itself, forget parameter estimation, we had 2 different pipelines that had been reviewed and tested on simulated data and real data. We had independent review teams. We had done injection tests with blind and double-blind exercises, etc. So inside the collaboration.
Of course, having multiple cases.
And then
that's
once we
true.
had multiple
But I was just
cases.
curious.
But now so specifically with what happened with the group from Niels Bohr, where do I start? So there is, first of all, the way they're doing the Fourier transform, they don't know how to, they're making a fundamental mistake in how they're doing the Fourier transform. We have explained this to them 10 different ways. They're not listening. I should say the graduate students and the postdocs are listening, but some members of the team are not listening. Now, there is another problem that we created. And what we created is that we released the data, the real data, but we did not release the correct maximum likelihood waveform that fully removes the signal. Instead, we released the waveform that we used to make the plot that just happened to be lying around and it was convenient to put out in the open. So that was our doing. And what happened there is that they used that waveform, and there were residual left, combined with the fact that they applied the filter wrong in their Fourier transform, created correlated noise, because yes, there was correlated things. They removed the wrong waveform and they did the Fourier transform wrong. So yes, they ended up with correlated noise.
But anyway, that was so a tempest in a teapot.
Yes. So we have explained this a gazillion of different ways, but there are get published, etc. And yes, we were this close before the double neutron star came to having written a paper for submission to a journal explaining all of these things. That was not going to be exactly against them. We were trying to stay above and be a tutorial about how you do our data analysis. And then the double neutron star came. And guess what? Our people wanted to work on our data analysis and not write that paper. So now we're going back, and that paper is going to be written and submitted to the literature. And yes, we're going to clarify all of these things. But we have more exciting things to do.
It's nice to get it clarified.
So.
So on that note, let's thank Vicky again, and we'll check you in the 8th floor in the East Wing.
Thank you.
So how many of us are on the 4,000?